Well, hello, Earth scientists. Welcome back for another lecture. Again, this is the second part of a three-part series dealing with astronomy. This topic in particular is touring the universe. So this presentation will take us through an introduction of the planets within our solar system. We'll discuss the differences between terrestrial and Jovian planets, and then also we'll introduce why Pluto is neither of those. And we'll talk a little bit more about their specifics as the planets are defined with their size and distance from the sun. So that being said, let's just jump in. So the first slide I've prepared for you is really the overview. So as if you notice, right off the bat, Pluto isn't on the list, and we'll talk more about that planet a little bit later. But we've established that there are two families of planets within our solar system, and and abroad. We have terrestrial and Jovian. So terrestrial planets imply that they're made out of, they have a rock surface and they're rock material, much like Earth. So as you can see, some of the terrestrial planets will be Mercury, Venus, Earth, and Mars. Now, Jovian planets are a little bit different. They're gaseous, so they're made out of a gas. It can be frozen, it can be within its normal gas state, but it's still gas based. So planets we have there are Jupiter, Saturn, Uranus, and then Neptune. So the table I have below, oh, then obviously I say Pluto does not fit either of these categories, and we'll talk more about Pluto later. Yes, it is made out of rock. It is about 1/3 covered in ice, but its size is the problem that we have now that we're dealing with, and we'll talk more about that later. So on the table below, I have the planet. I also have it based on in order of its distance in astronomical units, or how far away it will be from the sun. I also converted that into millions of miles to put it in perspective. I've also included the revolution, or what it would be considered as its year. I also have its rotation, which is going to be considered its day, and then I have its diameter to put it in perspective. So as an example, we'll look at Mercury. So Mercury is about 0.39 astronomical units, which means it's about 36 million miles from the sun. Now, its year is equivalent to 88 Earth days, meaning that the revolution, the time that it takes Mercury to go around the sun, takes 88 Earth days. As we can see, its solar day is only 59. The solar day is 59 days. So ours is about 24 hours. Theirs, it takes 59 days for it to do a complete rotation. So very different than what we experience. And then I included its diameter. So let's look down at the Earth. We'll skip Venus, go to the Earth. Earth is 1 astronomical unit, about 93 million miles away from the sun. Our year, the time it takes us to go around the sun, is about 365 and a quarter days, and our solar day is 23 hours, 56 minutes, and 4 seconds. So then, moving forward within that, we can look at places such as Jupiter. Jupiter, 5.2 astronomical units. It takes 12 years for it to go around the sun, and a solar day is only 9 hours and 50 minutes. My favorite here is Neptune. Neptune is 30 astronomical units away, or 2.794 million miles away. It takes 165 years for Neptune to go around the sun, and each solar day is 16 hours. So, if you kind of look at just the idea of the year and how long it takes to go around the sun, and its normal day of, day and night, if these other planets had life, what would that do with its seasons? Think about that. That's why we find that many of these, especially Mercury and Venus, look at how long it takes for it to rotate from day to night. These planets are very, very hot. Mercury's hot because it's just super close to the sun. But when we think about all these other planets, what would that do if they had seasons? That's just kind of something to think about. I don't have, the best answer on that, but I guess kind of something I always thought about is like, wow, like it takes, their day is only 16 hours. So you have 16 hours of warmth and then 16 hours of cold. So how that rotates back and forth versus our 12 and 12 in that sense. So anyway, moving forward, we can look at the planets as an overview. So again, we have these families, so we obviously can distinguish them between either being terrestrial or Jovian, but we can look at the planets either being out of gas, rock, or ice. We can also look at the atmospheres of the planet. So we can see that some can have either very thick atmospheres because it's already gas anyway, or they can have very weak atmospheres, but just the right accumulation of gases. And that's the thing, is that even though we may have a very small atmosphere for Earth, it is the right amount of gases in order to keep life in existence. So it's the right amount, even though it's very thin. So I always think of our atmospheres as sunblock. So there's lots of different sunblock that's out there, and so it doesn't matter. You can slap and slather on a really cheap, high value sunblock. Even though it could be really thick, it's not going to do any better than maybe one that's really thin, but with the right chemicals that are within it. So those are some things to kind of point out. Again, we've already discussed this, but I guess I like this in a table form. Just putting the distance of, looking at, okay, this is Mercury, there's Neptune. These are the distance, if this is representing the sun, how far away everything is. Also in this table, they're showing temperature in Kelvin. That's just showing the melting rate. But if you guys think about just temperatures, it's the same idea. This is warm, and then it gets beyond freezing out in that point, because we can see this is where we break into just ice. But nonetheless, I guess like this is putting in a perspective that is more informative than something classic like this, because this just kind of puts everything together, but this actually puts it in the actual distance to kind of put it in perspective. All right, so that being said, let's start looking at our planets. So our first one we'll talk about is Mercury. So Mercury is the closest to the sun. It's, again, 0.39 astronomical units from the sun itself. It is actually the smallest. It's about the same size as the continental US. So that's, all of the, all masses that represent the continental U.S., so which excludes Hawaii and Alaska. The surface topography is very similar to Earth, and also the moon, and the fact that it has craters and highlands and lowlands. There's also ice identified within some of the craters in the darker, deeper spots. So even though it is closest to the sun, there is still ice in existence. Well, why does that range? Well, it's because its surface temperature has the greatest extremes of any planet. So it can be 840 degrees Fahrenheit, or it can be negative 257 degrees Fahrenheit. So there's a very big dramatic change between the highs and the lows. Our next planet we'll introduce is Venus. So this is about 0.72 astronomical units from the sun. It's known as Earth's twin. It's about the same size, just a smidge smaller. The surface topography is covered with very thick clouds that prevent the visible light and radiation being emitted from the sun to be absorbed on the surface. But that being said, once you can observe beyond that atmosphere, we can see that it's mostly volcanic flow plains. The surface temperature is 870 degrees Fahrenheit, mostly because it's still made of volcanic plains, and the atmosphere is about 97% carbon dioxide. So when you think about just that alone, we know that the more carbon dioxide you have in your atmosphere, the more humid and warmer it will be, because it's a greenhouse gas and traps that radiation in. So that also contributes to its heat. Maybe one you've never seen before, Earth. We're 1 astronomical unit from the sun. The equatorial distance, so the distance around the Earth, is 24,901 miles, making it the largest of the terrestrial planets. The surface topography is unlike anything we've seen anywhere else. Why? Well, because we have oceans, we have sea surfaces, so we have basaltic oceanic crust, we also have granitic continental crust, so we have this variation of we have hydrosphere, atmosphere, biosphere, and lithosphere. So we have all these spheres, and because of that, we're able to then be the only planet that has observed life. Again, our average surface temperature is about 63 degrees Fahrenheit, much more habitable. Next planet will be Mars, and Mars is about 1.5 astronomical units from the sun. It's the second smallest. It's only about half the size of the Earth, but what's interesting about it is that its superficial topography, there are in the northern area, the region of that planet, are lowlands, which the topography has been shaped by lava flows. The southern region itself is more mountainous and an incredible amount of meteor impacts, and so within these large craters. I found this cheesy image where it shows, again, North America kind of planted there on the planet itself to kind of put it in perspective. The surface temperature is really unique. The atmosphere is only 1% of the density of our own atmosphere. That being said, it experiences what we consider extreme weather systems in the sense that they get dust storms that occur, and they're so large that it can actually change the perspective of its observation from Earth, so it changes the color. Again, the temperature ranges between negative 195 degrees Fahrenheit to a very nice 75 degrees Fahrenheit. Um, there's also been some additional research with Mars, as you know, and they've learned that there is possibly and probably an incredible amount of water on that planet. The problem is that it's underneath the surface, and it does not get exposed until it gets cold. And when water freezes, it expands, and it can actually excrete through some of the craters and some of the cracks within the planet. The problem is that's going to be on the dark side of the planet, so it's harder to observe that. Another thing that was kind of interesting is that we first started getting our better images of it. We saw an amazing amount of landforms, most of which we learned were fluvial, meaning that it came from running water in rivers, such as alluvial fans. So we did learn a lot more about Mars and the fact that there was and probably is still water, even though it has a very weak atmosphere itself. Now, moving into Jovian planets, we'll look at Jupiter. Jupiter is about 5.2 astronomical units from the Sun. It's about 11 times the size of the Earth. The diameter alone is 88,000 plus miles. The atmosphere, well, what's unique about it is that it's pretty much 90% hydrogen, then a mixture of other greenhouse gases. But what's most observed about this is the Great Red Spot, which is this guy right here. And that red spot is not just a an awkward discoloration on the planet. It's actually a storm system. It's a cyclonic storm system, very violent, and it takes 6 Earth days for that storm to just rotate one time around. The reason that storm still exists and has been observed for over 100 years is because of the speed in which that planet is spinning, because of the Coriolis effect. As that Earth spins, it deflects things. And that deflection continues to feed the energy of that storm. So it will continue to rage on. Our next planet will be Saturn. Saturn is 9.54 astronomical units from the Sun. It's about 9.5 times the size of Earth, so it's quite large. Its atmosphere, well, their winds are over 1,500 kilometers per hour. Very large storms have been observed as well, but the thing that people see and observe most about Saturn are going to be its rings. There are thousands of individual rings. The composition ranges from ice to particulate matter. They've broken the rings down into 3 different families. But the idea is that you have this particulate debris, whether it be frozen or whether it be of mass, and it gets caught within this gravitational zone within the ring, and then it stays within that zone. They have also observed rings change color, change densities as they merge, and that's implied that it's dealing with gravity. Next planet is Uranus. Location 9.2 astronomical units from the Sun. It's the 3rd largest planet. About 63 Earths would fit inside that planet. It's known as the Great Ice Planet, which implies and also results in its very unique coloration of its very white-blue mix. It's about negative 153 degrees Fahrenheit. It's also known as a sideways planet. So most of our planets have a tilt, where this is the north and this is the south, and they're tilted like this or tilted like this, whatever it might be. But this one is actually going this way, which means it rotates this way. So it's the sideways planet. The axis of rotation is nearly parallel with the plane of its orbit. And then a fun fact, one trip around the Sun takes 84 years. So it takes 1 year around for 1 year to equivalent for that planet. It takes 84 Earth years to go around. The next one is Neptune. Neptune is 30 astronomical units from the Sun. It's about 3.9 times larger than Earth. The atmosphere itself is mostly hydrogen and methane. The average temperature is negative 353 degrees Fahrenheit. Extreme weather and winds will often exceed 700 miles per hour. This is one of the slowest, as we can see. It takes 164 Earth years for that planet to go around. It's obviously, the name Neptune is because not just the color, but it was named after a god of the ocean. So again, it's frozen, frozen, frozen. And then our last one, planet X, Pluto, neither terrestrial or Jovian. So it's almost 40 astronomical units from the sun, so it's really, really, really far away. And it becomes very challenging for us to study because it's so far away. It's about 1/6 the size of Earth, which means it's actually smaller than our moon. And that was really the deciding factor as to why it doesn't quite categorize itself as a terrestrial planet. Um, so it's being identified now as a dwarf planet, meaning it's just really small. It is not a gas planet. There's actually land mass to it. It's about 1/3 water, frozen on the surface that we can see, but it's made of both then ice and rock. What's interesting about it is we really didn't know a lot about it until just recently when we were able to scan some photos from a satellite that was going out of its orbit and they were hoping to be able to trigger it. So one of the last things it would shoot would be a flyby of Pluto. If you like dramatic documentaries, there's a very short TED Ed video that shows the challenges because in the process of getting that satellite to take photos, they lost contact to that satellite and they thought, well, then we'll never get photos of Pluto. And then right at the last minute, the computer system picked up, they were able to get a tremendous amount of photos in a linear line along the planet, and it blew people's minds because it actually has a landscape. There are very clear, identifiable, geomorphic landforms on that planet. And so that was like really the nail in the coffin that, okay, we agree it's not going to get the full name terrestrial because it's too small, but it is a planet, and it does have a landscape on it that's more than just craters itself. So then lastly, I wanted to throw this in. So we've talked about these planets and then wanted to bring in their tilts. As you can see, Mercury has no tilt, Venus has a slight tilt going this way, Earth goes that way, Mars goes that way, Jupiter's very little tilt, which drives its weather system. Saturn has a tilt, there's Uranus almost at a horizontal plane, and then Neptune. Now, why do these planets have tilts? That's a great question. So astronomers think that each planet had developed its tilt generally during its formation as a planet. When you're forming a planet itself, you're taking in a lot of this debris, terrestrial and extraterrestrial debris, and it's being pulled in together as a mass, and then therefore you're going to be hit, assuming you don't have a very good atmosphere, by asteroids and comets, and that occurrence will cause the planet to tilt. So that's why it's generally and believed and agreed upon that the reason that Earth has its large tilt was because of an extraterrestrial mass the size of Mars hit the Earth, knocked it on its tilt, removed a bunch of material that would then turn into our moon, and there we are today. Now there are other things that deal with tilts, because obviously the tilt itself can affect the season that the planet experiences. You don't remember that? Go back to our lecture about the reasons for the seasons. But the tilt can also wobble or change. So there's different cycles that our tilt can experience. So as an example, when looking at the Earth, we have 3 cycles that the Earth goes through. We discussed one of them already, looking at precession, which is if the Earth is like a top, sometimes it might wobble a little bit. So it's still 23, but it wobbles this way. There's also been occurrences in which we find the tilt has changed, because even though everything is in motion, it will remain in motion until stopped. But that doesn't mean that it's always in line like we would like to think. I always compare stuff like this to like blinkers on cars. Like you get off the freeway and the car in front of you has their blinker on, you have your blinker on, and then it just looks like everything is perfectly in sequence, and then it doesn't, and then it does, and then it doesn't. And it's because it was never really in sequence to begin with. And so because of these Milankovitch cycles that we experience on Earth, we can actually trace back a lot of our larger glaciations, ice ages, and stuff like that on top of just climate conditions, but looking at these Milankovitch cycles that last between 20 to 40,000 years between each cycle. So pretty neat. So recap, what did we talk about? Well, we introduced the planets within our solar system. We'll talk more about that the last presentation we got together. We introduced their importance. I'll go back to the slide here. So we talked about their names, their distance, which is relation in miles, the revolutions, the rotations. Am I expecting to memorize all this stuff? No, by no means. I can't. This is a very short course that deals with this, but I expect you to understand the order in which the planets are. I also expect you to understand the values of astronomical units, the differences between revolutions and rotations, and then to just really be able to, if someone asked you, to very quickly give a one-sentence description of each one of these planets, could you do so? With some information for a short answer, I certainly believe that you could. You could, oh, well, let's talk about Mercury. Well, Mercury is the closest to the sun, is the smallest planet, and it's very similar to Earth because it's cratered and it's about the same size, blah, 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 blah. So you could do stuff like that. Very simple, just so you understand the order, the general information, and things along that line. Well, I hope you enjoyed this. I appreciate your contribution and time as we're talking through these modules, and we'll talk soon.